We just finished the presentation of this morning by talking about these things here, the dinosaur, which are always branch, and I was explaining that in fact, do you know what means dinosaur in Greek? What? Dinosaur means terribly big, okay, in Greek, ancient Greek. So this was clearly the biggest animals that we ever seen on Earth. And as I said, many paleontologists actually are thinking that during the Upper Jurassic, the birds were deriving from the theropods through the Archaeopteryx, somewhere here, and we can say evidently that birds are still living dinosaurs. Okay, so not all dinosaurs have not disappeared. All dinosaurs have not disappeared at the KT boundary. And I was also showing that the mammals here appears from groups, the synapsid and reptile groups around the upper Triassic. But this is something that we may see tomorrow. Okay, this afternoon, now I will give you some details about the, let's say, larger mass extinction that the world have known since the beginning of the Phaeozoic, since 540 million years. And this is the Permian-Triassic mass extinction or end-Permian mass extinction, which is here, please. Sorry. Thank you. We have here so a maximum of intensity extinction that you have here. And you can see here that this is a percent of genera, and here almost 80%, maybe more, of the genera got extinct some 251 million years ago during the Permian-Triassic transition. You can also see here that there is not any meteorite known for that extinction, not even before, not even after, but there is a huge volcanic activity, mainly predating during the Upper Permian, but also right at the Permian-Triassic transition. That's to say, right at the transition, right at the mass extinction maximum. So note also this white band here. This is the presence of a huge black shale deposition, meaning that, as you will see, anoxic condition or even euxinic condition. Euxinic means that the oxygen minimum zone, so the anoxia, reach the surface of the ocean and may even lead to some kind of sulfur hydrogen eruption, as you will see. This is a nice theory which may explain how you may destroy the ozone layer through intensive anoxic euxinic condition at the surface of the ocean. Okay, so let's have a look on that extinction this afternoon. Let's start first by that slide. It's you can recognize here, well, long time ago, 1860, already Phillips, this is an English paleontologist, have seen here, was doing a separation between the Paleozoic life and the Mesozoic life. And the change was corresponding to the Permian-Triassic boundary. So this is not for nothing that long time ago, the paleontologists more or less were separating the period, the Paleozoic, from the Mesozoic. This is due to the fact that at the Permian-Triassic boundary, you have a complete change in fauna. And you can also see that during this time, the same Phillips has more or less seen the same thing for the Cretaceous-Tertiary boundary, separating the secondary era to the tertiary era. So all these things are well known from the fossil record since a long time. Okay, but this was really a crucial period. Why? Because here you have a view of what was the Paleozoic marine life. Mainly, you get a reefal community with epiphyseal brachiopods, meaning that they are living on the seafloor and not burrowing too much. Some brachiosaurs, sponge, crinoids, and only a few cephalopods, bivalve, and gastropod. What does it mean? It means that the fauna was mainly composed of fixed taxon, meaning that they cannot escape, they cannot move if you increase the stress, for example, due to anoxia. They will stay there and they will die, okay? And you have just only a few cephalopods and some bivalve and gastropods which were able to move, but not so many things. And when you enter, after the Permian-Triassic crisis, to the Mesozoic, we can say that this is a modern ocean. Clearly a modern ocean, fully different. The community here, as you can see, here is made of increasing mobile taxon with echinids, which are quite mobile, gastropods, but a lot of swimmer, nectonic guys like cephalopods, also crustacean, and some epifaunal, but also a lot of bivalve able to burrow more or less into the mud. This Mesozoic life is very, very close to the modern ocean. And that's what we can say, that the transition from the Permian-Trias, in fact, is a transition from Paleozoic, ancient ocean, to a modern one. A transition from an ocean where the benthic life was dominating to an ocean where the life was a lot more mobile, if I can say that. This is very close to modern ocean. Okay, so, this is more or less sum up the content of that presentation. I am starting actually an introduction, and we will see first really in detail what is the geological content. We'll see the stratigraphy, the paleogeography. I will show you some boundary sections, and we'll discuss about paleogeography, but also sea level changes. And after we'll discuss a little bit the paleontology. And here I will use some kind of comparison between a piece of music, in fact. This is a Farewell Symphony that we can translate in paleontology if you want. Stress on biosphere. And this Farewell Symphony is quite interesting. I will explain that later, but I can already tell you that, in fact, this is the last movement of this symphony. Each musician is leaving the stage one after the other until nobody is left. It's a little bit what happens during the Permian-Triassic mass extinction. So, but we will see this in detail, and we'll see what went extinct in the marine domain, what went extinct in the continental domain. Okay, and after, we will try to explain that and to see a little bit the mechanism. And we will see what are the geochemical evidence, what are the climatic change, the sea level regression, a huge regression at the end of the Permian. And we'll talk about the salinity of the ocean. We'll talk about evaporite, as you will see, because the end of the Permian was a time of a very arid condition in terms of climate. And we'll talk a little bit about cosmic radiation and Bolin impact, even if there is almost nothing here. And clearly volcanism, transgression, and anoxia. And after, I will use another image, another picture, another comparison, which would be the Orient Express Crime. This is a book of Agatha Christie. It's an English writer, and she is writing books about where you always have a murder. This is quite known. I don't know, but maybe not in India, but on the European TV. You have a lot of series named The Adventure of Hercule Poirot, which is a detective. And I will make some kind of comparison with this book, because I will see it's a little bit the same story. And now, just a few books that you may read. As a reference, Erwin, The Paleolithic Crisis, Life and Death, the Permian. This is an excellent book about the Permian-Triassic mass extinction, but not really fully available on the web. But Allen and Vignal, Mass Extinction and the Aftermath, Oxford Unity Press, is a really excellent book, because it's a really nice sum up of all what I am more or less trying to teach about mass extinction. And if you want, I have the PDF here on my computer from the Hallam books. If you want, well, if you are a Nubes key, I can make you a copy. There is no problem. I can do this for you. Just give me your key, and I can just transfer that file. The next one is in French, not very interesting for you. And after, well, there is many papers on the Permian-Triassic, because clearly, when you have 96% of the species which are wiped off of the surface of the Earth, a lot of people is trying to understand why and how. Okay. So now, just let's see where we are on my chronostratigraphic chart from the International Commission of Stratigraphy. We are exactly here. So the Permian-Triassic boundary, the age, is officially by now 252 million years, 0.17 plus or minus around 60,000 years. This is a very precise age, because you will see that very close to or at the boundary we have some hash layer, some bentonite with zircons. Okay. You also see that the name a bit strange, Wu Sharpingjian, Cheng Jinsheng, all this is coming from China, because the GSSP, the official section type, is in China, in Meishan. And there is also some other stage, like the Hindu one, which is probably from India. I don't know where exactly, you have to tell me. But it looks like, at least the name, because there is some Permian in India. Right? Okay, so this is more or less the international chart. Now, if we try to put a little bit more age, more biostratigraphy, okay, what people used for dating this Permian-Triassic boundary. This is the base of the Trias is marked by the apparition of an ammonites, but it's not very good, because the ammonites are very endemic. Why? Because you have seen, I will show you this in more detail, but we have one single continent, so clearly there is a huge endemism of the ammonites living to the west or east of the continent, and because they were clearly separated for million years, so it means that you have a different evolution of the species to the west and to the east, which are separated by a huge continent. There was not really a good possibility for them just to cross and to mix up. So it means that if you are in Russia, and, the biozonation of ammonites will be quite different from the one that you are using in, for example, North America. We have to be aware of that. It's quite important. But a better group as a conodont, and all the Permian-Triassic mass extinction event is based, the term of dating, is based on the presence of this conodont, which allow a very precise biostratigraphy. People also are using brachiopods, bivalve fusilinids, which are these giant foraminifera that I just showed you this morning. But the problem, as I said, it's very difficult to connect the Tethyan to the east, to the Boreal realm, to the west, because there was a huge continent in between. In terms of duration, well, this is the date, more or less the exact date of the transition. The duration of the Permian is quite long, 47 million years. Trias duration is longer, 51. And okay, let's say that the mass extinction is maybe a short event, 200,000 years, maybe a little bit less. But the more or less the timing, the interval of time where you have very low biodiversity is really, really long. Probably some 60 million years. The recovery during the Triassic was really, really long. Okay, so as I said, ammonites are not very useful due to endemism, but we thanks a lot the conodont. So these are this fragment of jaws or teeth, if you want, belonging to this very strange animals, which was some kind of very primitive hemichordate, probably the ancestor of the fish, maybe our ancestor, if we go far away. Okay, in terms of paleogeography, as I said, I show you this morning that since, let's say, the Devonian through the Carboniferous and the Permian, you have the aggregation here of a huge continent here, the Pangaea, okay, which made partly of Laurussia, Gondwana. And it means two things, clearly, that you have a Paleothetis here to the east, which is never mixed with the Pangaea or the Boreal zone to the west, okay? So that's why a lot of fossils are endemic here. And especially, clearly, this kind of continent is not very rich in different ecological niches. Meaning that for the marine life, the possibility to escape to more or less the increasing stress due to that extinction was very difficult. But you will see that during the early Triassic, this part of the Paleothetis was almost empty of life. And there was a migration of fish, amphibians, and so on, toward high latitude in order to escape to a huge, huge warming period that we have during this time. So this is for the late Permian, and well, for the early Triassic is a little bit less complicated due to a more cosmopolitan distribution of ammonites. There is a more mix-up of the ammonites, okay? So we are able to make better correlation. And you can see this is the birth, the rise of Tethys Ocean, which will grow up through the Jurassic and the Cretaceous. But note that this was really a single continent, the Pangaea. So this may explain the, let's say, severity of the crisis. This is a very particular paleogeography. Okay, now in this particular geography, I have to locate a little bit the sections, the stratigraphic section that we use in order to, well, try to understand that crisis. So here these are more or less section. I don't want to show everything. You can see that, boy, clearly the continent not exactly the same place as today. India was there, for example. Pakistan is here. The very section in both land. Central Iran, lots of nice section, marine section. Armenia, shelf section. But the best are in South China and in the Southern Alps, in the Dolomite mountain chain. East Greenland, Spitzberg, and Canada, where really the place where you have very nice marine section. For the continental one, well, it's a little bit more difficult, I would say. The continental one are located mainly in the south high latitude, East Antarctica, East Australia, and the famous Karoo, South Africa. And here, this is the place where we get some fungal remains, because there is a fungal spike. I will explain you later this. But you see the place, these are the stars where vertebrates are present as not so many. And the same can be said for the plants. So, well, we don't really know so much about, more or less, the terrestrial domain and the evolution of plants and vertebrates on this terrestrial domain during that extinction mass. Okay, so now let's go first here on that paleographical map. I have to go back. Okay. Okay. Let's go first to the Southern Alps here. Northern Italy, the Dolomite, which are huge mountains made of, as the name is indicative, Dolomite. And you have a lot of Dolomite, a lot of carbonate with a not very deep section during the Permian. And you can see here these are carbonate with oolite. And suddenly here you have the occurrence of this horizontal line, meaning that you have black shell. You have the disappearance of the carbonate and the appearance of a lot of black shell here. And this black shell corresponds also to a huge negative delta C13 that I will explain later. And so you have coinciding with this change with the appearance of very finely laminated micrite, which is enriched in organic matter of anoxic condition, marked by pyrite thromboids. I will explain that later on what it is. Laminated, no bioturbation, so no oxygen on the seafloor. A lot of pyrite and some autogenic uranium like vanadium, but also molybdenum, when they are present, indicate a very low oxygen condition, anoxic condition, because they cannot be fixed where you have too much oxygen. So when you get these trace elements in the sediments, it means a huge anoxic condition. And here, this is a location of the Permian-Triassic mass extinction and the boundary. And there is something which is very interesting here, but you can find in a lot of places, not only here in Italy. This is a fungal spike, mushroom if you want, spores. So it's a level or several levels with a lot of fungal spore and pollens, and meaning here that you know that mushrooms are pioneer. Okay, so when you, for example, you have a wildfire in the forest, you destroy all the trees, all the vegetation. The first to come back are generally the fungi. And, well, it's very well known after a volcanic eruption, for example. When you get that, it means that probably a lot of the vegetation were completely destroyed, or at least suffering a lot. Okay, and in order to start from shallow carbonate into quite deep laminated micrite enriched in organic matter, you need a deepening. In fact, the end of the Permian, the beginning of the Triassic, is marked by a huge sequence boundary, starting from a regression to a huge transgression. And this huge transgression will propagate the anoxic condition well onto the shelf, which is probably very detrimental for the biosphere too. Okay, and here this is probably the most incredible GSSP point that you can find in the world. China is apparently a very well organized land. As you can see, when they obtain a GSSP, it's a monument at the end, okay? Because they made all this building for this boundary here, that you can see here, that you can see here. This is really a monument, okay? And here, this is really funny, they put a giant ammonites and a really giant conodont here, because normally a conodont is less than 1 millimeter in size, and this one is 10 meters in size. So really nicely done, and I visited these things, and well, you can walk here. There is an indication of the section. There is a golden spike that you put at the base of the Triassic, and here there is a lot of quarries where you can sample as you want. This is probably the most incredible GSSP that you can see. It's very well done, thanks to the China Geological Survey. And I have to say that, for example, the KT boundary GSSP in Tunisia is not very well preserved. It's very difficult to find it sometimes. The same, and a lot of GSSP are not so well preserved as China did. So really nice work. Okay, and what you can see also is here, this is the appearance of this very finely laminated shell and mudstone, indicative and black, indicative of clearly anoxic condition, and the presence of a bentonite layer that you have here. And this bentonite has been very well dated, and you can see that we are quite close to 252 million years, which is more or less corresponding to this huge mass extinction. Another view, it's in the book of Alam and Vignal, which are probably two of the best specialists of the Permian-Triassic boundary, especially Vignal. And here they show, but this is exactly the same section. They show some carbonate at the base, and after you have clearly a change into this formation from carbonate ridge to a black shale ridge, and Permian-Triassic is somewhere here, and you have the presence of more or less this black shale, meaning super anoxia, and the presence of marls on top, and the presence of these hash bed layers, which has been dated at 252 million years ago. And okay, this is here that you have the last appearance datum, so the last presence, if you want, of ammonites and conodont from Permian, and here the first appearance datum from conodont parvus, which mark the base of this first appearance datum, mark the Permian-Triassic boundary. This is the base of the GSSP, the base of the Triassic. So the duration of more or less of the sediments exposed to that picture is probably less. It depends a little bit from the dating, but less than 500,000 years. It's probably closer from 2 to 300,000 years. Okay, so it means that you have several things here on that picture. One thing which is quite clear also on that picture, here's the fact that, well, you have, and this is again taken from Alan and Vignan book, you can see here that the Permian is corresponding to a huge regression, and here you see more or less the proportion from marine, and non-marine sediments. So clearly the top of the Permian here was clearly a regression, and also you can see that the Triassic was transgressive, a huge transgression, which may explain more or less again the propagation of the black shale, of the anoxia or euxinia almost everywhere in the global ocean. Okay, so a little bit of paleontology by now. What are the victims in the sea? Victims in the sea are the following. A lot of ammonite died out. Trilobites were really affected. Corals. You will see that these guys were completely wiped out of the surface of the ocean and this for a few million years. They will reappear only around 5-7 million years after the crisis, which is just incredible. It means that really the benthic environment, the shallow environment, they are really, really affected by that crisis. And well, you have other victims like brachiopods. Remember that the Paleozoic was a golden time for the brachiopods. They were really very highly diversified, a lot of families, genera and species, and for them this is close to the end too. The same can be said for the Radiolarian, but the fusulins are this big foraminifera, which can be big like that. Just think that it's just one single cell, went extinct during this time. That's why, in fact, now if I'm talking again about this comparison with the Farwell Symphony, that we can translate as stress on biosphere, if you want. The comparison is the following. This is the way in which many Paleozoic life forms disappear towards the end of the Permian. It's a little bit like this piece of music from Joseph Haydn, where during the last movement of this piece of music, one musician after the other takes his instrument and leaves the stage until at the end no one is left. It's a little bit what you will see. It's a twofold mass extinction. It's a little bit like that. You have a gradual deterioration. When I say gradual, this is over a few million years. Deterioration of the environment during the Upper Permian, leading to a threshold where nothing almost is left. So I think this is quite a good comparison. Okay, so let's go to see a little bit in details in what happens in some of the groups here. You can see here that, for example, brachiopods show a really catastrophic extinction, but at the beginning, this is quite gradual. As you can see, we start some 2 or 3 million years before, and you have an acceleration here around 500,000 years before, with really a minimum of diversity reached in the earliest Triassic. And look, you start from almost these are genera, 60 genera, to almost 0. Okay, so interestingly, if you see there is two kinds of brachiopods. I don't know if you are familiar with these animals. One is articulate brachiopods, meaning, and these are really the most diversified group. It's like where you have the Spiriferidae, Terebratulidae, Rinconidae. So two last one are actual one. They are still surviving, and they were present during the Permian-Triassic transition. And you have the here in Articulata, which is living fossils, which appears at the Cambrian, and this fossil is very particular because it's living very deep in the mud. And that's why these fossils, it's a living fossils, we can say, because it survived to any crisis, because it was living very deep into the mud, escaping more or less to the maximum of the stress, for example. So these Lingulidae, which are still actual, you can find them actually, cross since the Cambrian every crisis without any change, not change, but change, through all this time. This is quite interesting. For them, clearly, the situation is a little bit different. They are not protected by the mud. They are filtering, and they are living on the seafloor. They are fixed. They are not moving at all. So if you have a huge anoxy, all these people will die, very clearly. Okay, so this is the case for the brachiopods. Now, let's have a look about the sponges. Sponges is a little bit different because sponges, you know, are quite, let's say, primitive animals. They were appearing probably in the Precambrian, and they don't really change in the way of life, in their morphology. They use only 3-4 cellular types in order to live. In fact, this is like a bag, if you want, which has some little hole, and they just filter the water all around the animals as a sponge, and you have a hole on top, the oscule, where all the water is after ejected. This is the way. It's a very nice, simple filtering system. And they are able to live quite in deep environment. They don't need light, in fact. They don't need the photosynthesis to survive. They like the mud. And you can see here that there is some kind of a decline during the Permian, but after some kind of stabilization during the mass extinction event. So again, you see that some of organisms are suffering less because they have some strategy and to survive. And generally, I have to say that the most primitive is the form, the more change these animals have changed to survive. So it means that this kind of animals has not very specialized adaptation. They are able to live in any kind of environment. They are not too dependent, for example, for oxic or anoxic condition. So it means that what you see generally during mass extinction, it's not, I have to precise that it's very important because some paleontologists are believing that, I think it's fully wrong. It's not genetic return to more simple form. This is just a dominance of more simple forms, which is quite different. You don't have any evolution. Just means that all during this time you have the same primitive forms, but they are not very abundant generally, because over which are more specialized, generally, more complicated, are dying because they are too specialized. They are too dependent to the medium. That's the other one, which are more simple, and these ones will dominate. But doesn't mean that you get let's say a genetic back to more or less more simple forms, genetically speaking. It's not exactly the case. It's just a question of abundance of the species which are able to be adapted in any kind of medium. Okay, this is a sponge, and now I give you the example of the corals. So corals is exactly the inverse of sponges. They really like clear water, the blue water, not the brown dark water. They don't like the suspension because they are photosynthetic animals. They need light in order to survive, and they need oligotrophic condition. Oligotrophic condition means no nutrients, almost, clear water, and they also like warm, but not too warm water. Coral generally are living in warm water. There is some corals which are living deeper in the ocean, in cold water, but they are not photosynthetic. This is quite different. So here you can see that this is dramatic. Since more or less the middle part of the Upper Permian, you have really a drop, and they are disappearing in the last 100,000 years of the Permian. And here, there is another things. It's not only the warming, it's not only the fact that you have dysoxic to anoxic condition, but the fact also that the salinity of the ocean is changing. I will explain that this a little bit later on. So for the corals, you can see that there is zero here, zero, slash, nothing surviving up to, let's say, almost 8 million years during the Triassic condition. And this is something which is very particular to the Permian-Triassic mass extinction. Okay, so now if you made a small sum up of what happens, again, you will see that there is, in fact, this is almost, I will see later, a threefold extinction. And you increase, really, it's like this farewell symphony, you really increase the stress on the biosphere. And we start, in a stage named Guadalupian here, where you can see that, for example, not for the conodonts, but for the ammonites, there is already something happening here. And after at the Permian Triassic, but also some event in the early Triassic, okay? And if we take the corals, they are quite abundant in the lower Permian, but in the upper Permian, within the Guadalupian, they are disappearing almost, they are surviving and totally disappearing, then reappear later. The same for the calci sponge, the sponge which are calcareous, which are not, because all the sponge that are surviving are making their skeleton in silica. As you know, main part of the sponges are producing a silica, so-called spicle assemblages. But the one doing carbonate are not surviving too. Afterwards, we have the Bryozoan, huge crisis. The fusilids are completely destroyed at the Permian Triassic bound. The brachiopods show also this two-fold extinction. I will show you here, in fact, there is two main phases very close to the Permian Triassic. Echinoderms. Echinoderm is very interesting because echinoderm is very sensitive to salinity. There is a term in English, steno-alin, which is coming from the French. Steno-alin animals means that they don't stand if you vary too much the salinity. What if it's fresh water or hypersaline water? But it's very important because you're going to see that these guys here are almost disappearing during this first part of the crisis, during the Guadalupian. And they are, crossing the boundary, but with a very, very low diversity. And, after we have the gastropod and the bivalve are suffering a little bit, but less because they are more mobile, compared, for example, with the brachiopods. Now, I said what I will just go back. What we will do, we have seen there is one first starting point, the onset of mass extinction here, and we will see in more details what we have here, okay? So, and here, this is a very nice paper published in Nature Geoscience by Song et al. A lot of his works is done in China by now, because in China, it's, they put a lot of money in geology, I have to say, and they have thousands of people working on this kind of problems. That's why when you have 200 paleontologists working on this kind of things, you can produce this kind of evaluation of about more than 500 species, which is really a lot. And I have to say that maybe 30 years ago, China was not really in advance, and we were not very confident with all the data coming from their papers. But by now, this has changed a lot, because they have a huge program where, for example, they invite a professor from foreign country, but not just for 1 month, but to settle definitely in China. So you get very well paid, and that's why now a lot of data are coming from where. So what we see here, it's very interesting. You have the timing here. So the Permian Triassic boundary is here with the appearance of this conodont. And here you can see this is the more or less species weakness, but be careful. 0 is here, and so you increase the number of species here on the left part. And you can see here that you have, in fact, a two-fold extinction. A first one very close to the limit. So some gradual things here occurring, a huge one here, and after gradual things, and a second one, which more or less post-date around, it's not so much, as you can see. It's a question of 200,000 years. So it means that you have some pulse here. And these pulses are, for me at least, probably linked to volcanic pulse, as you will see later on when we go into details. So the first stage of the extinction, as I said here, occurred during the latest Permian. It was marked by the extinction of 57% of species, a lot of plankton, some benthic group, algae, corals, and so on. And the second one occurred in the earliest Triassic, and you have extinction of 71% of the remaining species. So in fact, in the details, you can see that this is gradual with some acceleration. And here I'm really thinking a little bit about the fact that this may be due to some pulse, volcanic pulse, occurring during this time, as you will see. And this is the same paper showing a little bit the same thing with some kind of illustration. You can see here you have the number of species, and this is the latest Permian extinction. You can recognize here the fusulinids, the rugosa, some corals, the trilobite, the radiolarian. And this is the second phase of the extinction, is the earliest Triassic, where you can see that brachiopods are suffering quite a lot, ammonites, and so on. So this is really a twofold mass extinction. Okay, and something which is also very interesting, we have an extinction of coal. Coal extinction. It's a bit strange as an expression. I agree with that. This is, but it's really a coal extinction. It's not a cool, but a coal extinction. And here you have a picture with the latest Permian coal in Antarctica. And after this latest Permian coal, you don't find coal formation on Earth during 10 million years, which is really a lot. So has the corals on the sea, which were reappearing very late in the Triassic, the plants probably on the terrestrial domain were suffering a lot. And this is probably due to wildfire and huge warming, things like that. This is not very clear by now, but you don't have any more Triassic coal in the first 10 million years of the early Triassic, which is quite important. Now, there is also this question of this fern spike, but especially here it's not really a fern spike, but it is a fungal spike. So it's these things here is explained. The duration is quite short. This corresponds to the boundary and right after the boundary. And you can see here that you have this is in French, but I can translate it. It's not really a big problem. The spores of gymnosperm are equal almost to 0. The spores of lycopod are also decreasing, even not very abundant. Acritarch, which is a marine, more or less, dinocyst, is also quite low in terms of abundance. But look at the cells and spore of mushrooms, the fungi, is really increasing. And also look that the debris in French means remain, microscopic remain of wood, burned wood, is also quite present. So here we really think that acid rain, wildfire, because it was extremely warm, did part of the job, meaning that probably acidification on land, and both on land and in the ocean, were responsible for example, the destruction of the vegetation, but also the disappearance of main part of the benthic fauna. Okay, now we will start to try to understand a little bit better this event. And here I will use several geochemical markers. Don't don't be afraid. It's a little bit complicated, but I will simplify at most, more or less, the explanation. I will not go into details about all these problems of isotopes, but there is a few things that we can see. So we'll, yes, well, we can make a short pause in 10 minutes, okay? So here, this is Permian-Triassic boundary, and this is delta C13 here. And you can see here that, well, this is quite positive, meaning that production is still working. One negative, and there is huge negative here. And you can see that you can have this in both organic and carbonate delta C13 shift, negative shift. What does it mean? That means that both reservoirs, the organic ones, the plants, for example, and the carbonate, which are the marine ones, were affected by this change. Meaning here that it's not only a crash in productivity, which is partly probably the case, but you have something different here. This is probably, as you will see, something different, increasing CO2 into the atmosphere, at least for the one which has been measured in organic matter. But I will discuss this later on. Here, this curve is the sea level, so huge regression and an increase. And this is the delta the delta 18 oxygen isotopes showing quite negative values, which are clearly linked with a huge warming. It was really, really warm. And now, if we have a look on, so, well, this is more or less explanation. There is different explanation. I will take this in more details afterwards. But what you can see here, that we have probably a crash in productivity and more CO2 supplied to the ocean atmosphere system in order to get these negative values for the carbon isotopes. And here, if we talk about the comparison between the delta C13 of carbonate, which became very negative, you can see that this is the green curve here. You can see that the red curve is also showing a very negative peak here, which is probably really linked to some huge pulse in CO2 that we can explain by different mechanisms that I will explain later. And well, for the delta C18, the delta 18O, you can see here that you have some probably cool condition, but I will explain to you that it could be explained in another way, and warmer condition for sure. But in addition, you can have, if you have a lot of CO2 into the atmosphere, more greenhouse, needing more rain. If you have more rain, you have more fresh water input here into the ocean, and the fresh water is more negative. So to me, it's a mix between warming and also the input of a lot of fresh water into the ocean. Okay, so we'll stop here for 10 minutes in order to have a tea. It's tea time. Okay, just a very short comment about during this small break about what you have to do, because you have some duty for Friday. Because Friday, I want you to speak to my place. I think I speak really too much. So there is two papers here that you just got. I will start with the first one here. This is our large igneous provinces affect global climate, sometimes cause on mass extinction, and represent a natural marker in the geological record. It's some kind of an abstract, as you will see, which has been done by a huge, really huge specialist, big specialist, Richard Ernst. He's really good. He wrote books like that, more or less like that, on the large igneous provinces. And Nasreddin Yubi is one of his colleagues from Morocco. And you will see that, well, the interesting things that he tried to take more or less well, there is some thing, but after he just take anything more or less in account. All the things that I explained during this week are there: global cooling, increased wildfire, destabilization of gas hydrate. We'll talk about that a little bit later on after tomorrow or tomorrow. Links with oceanic and oxic events, end of ice age, and so on. So it's really a very nice abstract, I think, that you can use. And you can read, and we may discuss a little bit about that. This would be the first part of the discussion, probably not the longest. But the second one is that paper that I really want that you read carefully, because this is about the definition of the Anthropocene, as we discussed later yesterday. Sorry. And you will see that there is a lot of discussion about the potential start dates for a formal Anthropocene epoch. And there is a lot of, let's say, discussion. Why do we have to do that? Why not? Do we have a good GSSP? And so on. And especially there is some figures like figure 2, which is really interesting. Maybe difficult to read because normally it's in color. But I will show you the same figure in color Friday morning, very probably, before the discussion. And here, what I want that to organize some kind of election, because this is time of election apparently here, but these are science elections, not political. I just want you say, okay, do you agree or not agree to fix a base for the Anthropocene? Do you agree to use the Anthropocene as an official stage, or do you just want it as a formal, saying, well, you can say we are living in the Anthropocene, but I don't care too much if we have to be really to introduce officially this term. So read carefully, especially that one, because after I will organize a vote about the different possibility to do that, because well, you can use the plutonium, you can use farming, you can use a lot of things that we will explain in the morning, and after we will vote exactly like the Commission did. I am curious to see that and to know a little bit what is your opinion about that. Okay, so just read very carefully, especially that one, please. By this way, we can organize a nice and small discussion. But we will go back to that paper in details during the presentation. I will explain really in details what we have in Friday morning, very probably. What is the limit to vote in India? It's 18, 20, 18? Okay, so you can vote, everybody, I guess. Okay, I think we can start again. Thanks for the tea. Okay, so on that slide, this is an explanation. We can try to explain a little bit how do you create a drop in delta C13, meaning that you enrich the seawater in 12. So normally, if you increase the productivity, this is exactly the contrary. The organism are taking preferentially when a foraminifera he is precipitating his shell. He is precipitating his shell in equilibrium with the ocean. That's why, in order to get this ratio, C12, C13, you need more or less to know more or less what is the ratio of the ocean. This is a bit problematic because you have to make an hypothesis, and you also need to know to use a standard. And the standard is a PDB belemnite from Vienna Museum that has been measured for the oxygen and carbon isotopes and compared. By this way, everybody is doing the same thing, which is very important because the spectrometer that you use to measure this isotope ratio can change, can be good, can be a little bit less good, cheap or very expensive, precise, not very precise. And it's very important to have to use standard in order to compare the data from one lab to another lab, because if it's not the case, this could lead really to big problems. So, in fact, here it's not an increase in productivity, because you see the contrary. You enrich the seawater in 12C, so you get a drop in the ratio, what we call the delta C13 ratio in short. And this drop can be explained by different things. First, a crash in productivity. If there is no organism present into the sea, well, you will drop more or less this ratio. As for the KT boundary, which is quite clear, here it's not so clear. But anyway, this could be the case. But you can also have a rapid influx of volcanic carbon, because the ratio of volcanic carbon is very negative. So if you had a lot of CO2 from volcanic origin, you will decrease this ratio. This could be an explanation. And after, there is this destabilization of gas hydrate. We'll go back to that in details, because for the Paleocene thermal maximum, we'll have a lot more explanation about that, because we know that here there is a huge negative delta C13 shift, which is probably linked to that phenomena, because we have some proofs here. Maybe. Why? Because we can infer that, because the delta C13 ratio of this methane, gas hydrate of methane, is very negative. So if you incorporate this natural reservoir to the global signature of the delta C13, it will be more negative, evidently. You can also have the oxidation of the biomass of the paleosols, for example, meaning that if you have a lot of erosion of the paleosols, you can deliver a lot of organic matter to the surface, and this organic matter will be oxidized, and the organic matter is again very negative. And you can have the rapid oxidation of organic carbon, the coal, for example. If the coal are reworked, they can participate to this negative shift. So I think all this way may have existed for the Permian Triassic, because you have volcanic activity, as you will see. You may have a destabilization of gas hydrate, but the proofs are not so easy to find. You will see for the Paleocene thermal maximum, it's a very nice demonstration that this was the case. Oxidation of the biomass, of the paleosols, of the coal, it's maybe something, but to me, I would rather think that this was that one, which was probably the best explanation. So yes. So now there is another isotopes, which is quite interesting to explain this Permian-Triassic transition and mass extinction. First of all, this is a strontium isotopes, 8786. The strontium 8786 is quite interesting because when it is let's say raise low values, it means whatever volcanic activity, or probably also more or less some kind of evaporite presence. And when you can increase that, it means here that you increase the weathering. Why? Because this ratio in old rocks, old basement, old craton is a little bit more positive. And this variation, this is a global signal that we can use in all the world. So in all the world, you have this swing here. So it's really a very nice correlative tool, and we can, there is a publication of a strontium curve for all the Phanerozoic, or from the Cambrian to the actual, where you can measure this strontium on conodont or on oyster, for example, and okay, you have the values, and you can say, okay, I am here. The date is somewhere in the Permian. So it's a really an excellent association during the last 500 million years. So you need to know exactly, a little bit more exactly where you are, because these values, you can find it in the Permian, but also, for example, in the Cretaceous. So you have to be a bit careful. But this is really a change from something which is probably more influenced by the alteration of basalt, for example, to something which see a lot of weathering from old cratons, where granite metamorphic the rocks are marked by this kind of strontium values. And this is a proof that during this time you increase the greenhouse condition and you increase the weathering on land. And the very interesting, so I was talking about that one, okay? So major increased continental weathering due to erosion, regression. And the next, this is sulfur isotopes. So sulfur isotopes, so that you can measure on pyrite, for example, is also very interesting because you can see that also, like the strontium, there is a huge change. But this change is more linked